Hi, welcome back. We're going to move on into the next step of this, which should be a pretty logical progression of the previous lesson. So, as a bit of a do now, I want you to take what you learned from the previous lesson, look at this reaction. Of course, everything that's missing a phase is either aqueous or, in the case of water, is a liquid. I just wanted to save some space because these redox reactions, they get a bit long. But go through and figure out which substance got oxidized and reduced and write a half reaction showing that oxidation or that reduction. I'm going to write down what I have here. So for the oxidation and for the reduction, all of the hydrogens and oxygens as +1 or -2. Second, we're going to go through and all of the group 1s are +1, the group 2s are +2. Third, we get to go through and we figure out everything has to add up to 0, which means that this chloride is a -1, this nitrogen's a +2, and this nitrogen's a +5. And then we're left with these two iron compounds. Now they are ionic, iron chloride, so we're just going to unswap them and use the ionic charge as the oxidation number. So for the oxidation, we've got iron +2 becoming iron +3. And to make the charge balanced out, we're going to have to add 1 electron to the product side so that the sum on both sides is a +2. And then for the reduction, we're going from a nitrogen +5 to a nitrogen +2, which means we'll have to add 3 electrons. We now need to balance this equation. I see 7 different compounds, and so that's going to be a lot of counting and going back and forth. This could be, for lack of a better word, nuts. But maybe we can use the half reactions to help us out. So I'm just going to copy down the half reactions again. The reaction doesn't happen in halves. So this whole reaction is happening at once, and everything we know about reactions says that there's a lot of conservation going on. There's 1 electron shown in the oxidation half reaction, there's 3 shown in the reduction. That's not balanced. We know that for conservation of matter, electrons in has to equal electrons out. Which means if the reduction is consuming 3 electrons every time it runs, the oxidation cannot be supplying 1 electron every time it runs. There's got to be a least common multiple between them for this to work out. We need to get these half reactions to a point where these 2 electron numbers are the same. We're going to multiply by 3, and what we get is our electron count is the same. Now, if we wanted to, we could add these 2 reactions. And then once you add chemical reactions, if you have any substances that are the same on both sides, they're redundant, you can cancel them out. The 3 electrons and 3 electrons cancel. This is good. This is what we want. We could be done if we were only looking at metal ions or elements. The issue is that the nitrogens and the irons are in a compound. The N+5 species doesn't really exist. You don't get a nitrogen with a +5 ionic charge. This is a nitrogen with a +5 oxidation state. Slightly different, but we can still use this. The iron to nitrogen ratio has to be 3 to 1 for this to work out. We can take these numbers that I wrote on the bottom in blue and we can insert them back into the equation where these elements occur. So this iron +2, I'm going to go to where this iron +2 is and I'm going to write a 3. This nitrogen is going to be a 1, so I'm going to put the 1 there. This represents a starting point for our balancing. So now we're going to attempt to balance the rest of it without hopefully changing these numbers too much. I count, let's see, the lithiums are good right now if I put a 1 here. The oxygens, we have 3 here and we only have 2 here, so we could put a 2 in front of the nitrogen monoxide. That would throw the nitrates out of balance, so we don't want to do that. Now this 2 here means we would need 4 of these. Are we balanced? I forgot these chloride ions over on the iron. So we have 9 here and 1, so 6 and 4 is 10, and 1 and 9 is 10. So we're actually balanced, and we're good. Yay! This doesn't really represent too much more work from the previous lesson, but it does give you a nice opportunity to string the whole process together and go from an unbalanced redox reaction, identifying it as redox, turning it into half reactions, multiplying the half reactions, putting it back together, and then finishing the balancing. So I'm going to walk through this one with you guys. This is one that we saw in our previous lesson when we were writing the half reactions. we're going to go through the same process. Figure out what got oxidized, figure out what got reduced, write half reactions and balance them. So iron's a 0, oxygen is a -2, hydrogen's a +1, +1, -2, +2, +3. This adds up to -1. There are 4 of those. It's -8. That has to be a +7. We did this in the last video. If you need to see me walk through that again a little bit more slowly. For the oxidation half reaction, nope. That's not what happens. Boom, boom. For the oxidation half reaction, iron 0 will become iron +3. And so you need 3 electrons on the right side for that. For the reduction, a manganese +7 will become a manganese +2. And that needs 5 electrons over here. And again, we have our issue where our electrons are not balanced. So in order to fix that, we've got to do, again, a multiplication, least common multiple. So we've got 3 electrons being reduced from our oxidation, 5 being taken up by our reduction. Our least common multiple should be 15. And frequently what happens is this number on the bottom, the reduction number, you multiply the oxidation by and the oxidation number by the reduction. I'm not saying that's all the time, though. It's better to just think of your least common multiple and get there in terms of electrons. And so then what you have here is 5 irons will make 5 iron +3s plus 15 electrons. And then here you'll get 15 electrons being consumed and 3 manganese making 3 more manganese +2. And so just again to make sure, we could add up these 2 reactions, but you see we're not including the H pluses and the waters. But what we have here is the 15 electrons in, the 15 electrons out. This is great. We are balanced. We've got that checkpoint met. So now next, I'm just going to take these numbers and put them up into the equation where these species occur. And we're going to put a 3 there and a 5 there. Let me clean this up a little bit. Now that we've figured out our oxidation numbers, let's clear those out so that we have room to count and think without this being too cluttered. I suggest using an eraser for this. Or I guess, I don't know, writing it in a notebook or something. Oh, I forgot a blank for these hydrogens. Oh no. I'll put a blank there now. But now we can see that what we tried to balance before, we only tried to balance the hydrogens and the waters. But now we actually have a nice ratio between the irons and the manganese. And this oxygen in the permanganate is what we're going to use. There's 12 oxygens here, so we're going to put a 12 here. And now there needs to be a 24 squeezed in next to the hydrogen. And just to make sure we balanced it right, remember that when we balance, it should be balanced for mass, but also for charge. The total charge on our left side, we've got 3 minuses, 3 minus ions, 24 plus ions. This is a total of plus 21. There's 3 2s and 5 3s, so that's 15 and 6, which is also plus 21. We're balanced for mass, we're balanced for charge. This is done. So if we need some steps, first we're going to ID the oxidized and reduced species. Then we're going to write half reactions. Then multiply. I can't spell multiply, although I do like this tablet. Multiply half reactions to get electrons in equal electrons out. Use coefficients to start balancing. And then you would just continue balancing until you're done. You can go back and check at the end, of course, to make sure that you got everything what you need in place, but that's the process. And the only new part is really step 3. Everything else we've done before in either the previous lesson or way, way earlier in the year. So there's one more thing I have to show you. I'll give you 2 practice problems and then we're done. There's one issue to consider. I'm going to step through this a little bit more quickly. Our oxidation here is that a lead becomes a lead 4 plus 4 plus 4 electrons. And then for the reduction, we've got a chromium plus 6 plus 3 electrons becoming chromium plus 3. So we're going to multiply this by 4 and this by 3, and we get 3 lead. Nope, not plus. Erase. 3 lead will become 3 lead plus 4 plus 12 electrons, and then the chromiums will get 4 Cr plus 6 plus 12 electrons becoming 4 Cr plus 3. There is a non-zero number of cases where the oxidized or reduced species, and I told you to do this, has a subscript that you ignored in doing what I just did. And it's right here. And that's fine. You don't have to deal with it. There's 2 ways you can deal with this. One is to just realize that when you say 4 Cr plus 6s, that really means 2 Cr2 plus 6, or plus 12 if you want to write that. If you want to write it out that way, that might help with your balancing, to make sense with your balancing. Does that make sense? Yeah. I don't. Whichever number helps make sense to you. I think if you want the charge to be balanced, it would have to be plus 12. But that's not. I'm not saying that Cr2 plus 12 exists. I'm saying you might want to take the subscript down. I'm not saying that. I'm saying you might want to think of the subscript. If you need 4 Cr plus 6s and you've already got a 2 in your subscript there, you don't need 4 dichromates. You only need 2 dichromates, because 2 times 2 is 4. And then you would put a 4 over there. Or the other way to go about this is to bring the subscript with you while you're balancing. So a different reduction half reaction you could write is this. But you kind of have to like pre-balance it in terms of the reduction half reaction before you balance it between the reduction and the oxidation. If you go back and read textbooks, some textbooks, particularly like advanced like AP or honors, will actually just write the whole ion, and then you'll have to like figure it out from there, and you get this, and then you have to like add waters over here, and then you have to add hydrogens over here if you're in an acidic solution, and then if you're in a basic solution, you're adding hydroxides and waters. And you can kind of see, based on doing it this way, this longer process, where the H pluses and the H2Os come from. And actually what's kind of neat is this lets you have a discussion of this reaction happens in acidic solution and needs a lot of acid to happen, which might explain why things don't happen certain ways. I have a very long story to tell you about how I almost poisoned myself. Some other time I'll tell that story. Maybe I'll record a second video or something. But it's kind of neat, because once you actually look at half reactions that way, you start to see, oh yeah, this won't happen until there's a certain threshold of acid. My point is, that's a really lengthy way to do it, and I would not suggest doing it that way. But what you can do, if you want, is you can bring down the subscripts before you balance the half reactions, or you can bring down the subscripts after you balance the half reactions. It'll work the same way, because your end result will be the same. And I made a mistake here. This would have to be, nope. No, I had it right the first time. It's definitely 6. Definitely 6. This stuff is hard. Just gonna put it out there. This stuff is hard. If you're not careful and you're trying to like talk and write at the same time, you make mistakes. But what you can see is that when you don't bring the subscript, you get 3 electrons here. When you do, you get 6. So when you make your least common multiple, you'll account for that, and it will work out the same either way. And that's what I meant to say. So to continue balancing, we'd put a 3 here and a 3 here, and that means this would be a 14, and this would be a 28. So that's plus 12, that's plus 12, that's plus 24. We've got plus 28 minus 4 is plus 24. We're done. So you don't like, but this is why I like this way of balancing, because to balance these really complex reactions, you're not going to do it any other way. But when you have an even number there, this 2, this 3, this 4, it's something that you have to think about. Now, it's not wrong to say that you can use this method to balance, you know, a single replacement reaction, which is a redox reaction, or a synthesis reaction, which is a redox reaction. It's just overkill. It's like really overly complicated for not much else. If you want some practice, go find a couple of those reactions that you know how to balance anyway, and balance them this way to make sure you get the same answer. It's kind of nice when you have an easy problem because you know what the answer is supposed to be, to make sure you understand a more complex process. But as a final checkpoint to make sure we understand everything, why don't you pause the video, walk through these reactions, take through the whole process, and try and balance them to see what you can come up with. I really hope one of them doesn't get way more complicated. But we're about to find out. Hopefully you paused. Welcome back. I'm just gonna start. Like I said, once you do this long enough, you start to just see patterns that show up. So for the oxidation, the sulfur -2 becomes a sulfur 0. And for the reduction, that's a +5. And that is a, oh, this one is going to be annoying. An M+2. Oh, we're going to have to go back and talk. It's okay. If you had a hard time balancing this one, it's definitely okay. But this is going to become 3s2- -2. Oh my god. I need a quicker eraser. I think there's a button I can press, but if I'm not careful, the button I press is like the next slide button, and then it just skips. 3s0 plus 6 electrons, and this would become 6 electrons plus 2n plus 5 becomes 2n plus 2. So again, we insert these numbers. So there's an S here, we're going to put a 3. There's an S here, we're going to put a 3. There's an N here, we're going to put a 2. There's also an N here. So what's cool about this reaction is that there are some nitrates that do react and some nitrates that don't react. So some of the N's go from a +5 to a +2. Some of the N's go from a +5 to a +5. And so this is going to make the balancing a little bit more difficult, but if we do things right, it won't matter until the end and we can fix things very easily. Leave that nitrate until the end because we've got the things in place that we need to have in place. Let's start with the silvers. I think I have to put a 6 here. Now the issue is I just called for 6 more nitrogens and I only put a 2 in front of here. Since some of the nitrates are reduced and some of the nitrates are not, this 2 here only represents the nitrates that are reduced, and we're probably going to have to add a couple more. In fact, we should probably add more like right now. So this 2 here is correct, but I think I need to erase it and replace it with an 8 to make sure we've counted both the reduced nitrogens and the non-reduced nitrogens. Yeah. So now if we go back and we check the oxygens, we've got 24 here, we've got 18 here, 19, 20. So we should put a 4 there. And I think we're balanced now. I think it all works out. Now the other way for you to have done that is to, like I said, leave it for the end. The only problem is you probably would have had to go back and retool the water to make it work. So like for these practice ones, I'm finding ones that are exactly what we did before with just a little bit more. So again, looking at the second one, we can see we got some 2s there. Those 2s are going to cause us some issues, but I'm going to balance it the way I said before, where the first way where I said like ignore it and we'll take care of it later. I prefer that way. So for the oxidation, we're going from I- to I0 plus an electron. And for the reduction, we're going from Cr plus 6 plus 3 electrons. We're going to go to Cr plus 3. So this is going to have to be times 3. We're probably going to have to fix this in a second. And then we're going to get 3I- will become 3I neutrals plus 3 electrons. Cr plus 6 Oh. Eraser. Plus 3 electrons goes to Cr plus 3. I have 2 problems. I have, well, okay. So there's like several ways to get about this. I'll show you both. Okay, 2, not several. But I have 3 iodines here and this I2. So one thing you could do is you could say, well, I need 1.5 I2s, and you're going to have to fix that later. This would be a 3. Again, I need half of this, and this is going to be a 1, and then I can balance from there. The problem is if I say I have half of this, then there's a 7, and that's like 3.5, and then my brain starts to hurt. So probably what would have been best, now that I'm at this point, is actually taking a step back. And I think I'm going to do that. I said I was going to do the first way. I'm going to go back on that, and I'm going to change that right now. Change that. Change that. I think I don't have to get rid of everything, just many things. Okay. So instead, here's what I'm going to do. I'm going to write an I2. I'm going to put 2I minus, and that needs 2 electrons. I'm going to say that there's 2 of these plus 12. I'm going to need 6 electrons, and it's going to make 2 of those. Now we've got our good half reactions. We've got a 2 and a 6. We still have to multiply this by 3 and this by 1. So this will give us 6I minus become 3I2s plus 6 electrons. Yeah. And we're going to get, again, the same 6 electrons and 2 Cr plus 3s. Now if we go back and put in our numbers, this should work a lot nicer. 3, 6, and 2. 7, 7, 14. Did I do it right? 14, 8, 7, 6, 6. It's balanced. This is hard. I'm not going to lie. This is difficult. This is the biggest application of half reactions. There's a practical side that you're using right now to watch this video, whether or not you realize it. We'll talk about next time, but this is hard. This is probably one of the hardest and most like you need to double back. You can see how many times I erased. But if you just watch this, go through it several times, keep practicing, it will get easier. Thanks for watching.